going to be great. And so I'll leave you to that, and you'll see me back in a little bit. Don't forget, if you have questions, to ask them in the Q&A section so that I can ask them back to our speaker afterwards. See you in a bit.
Hi there. It seems I'm live, so nice to be here with you. Today, I'm Mateusz Front. I'm a co-creator of the Membrane Framework, and today I'm going to show you how we implemented a WebRTC video conferencing server in Membrane in Elixir. So let me start with some information about the WebRTC itself. So WebRTC is an open source standard for video conferencing that uses mainly state-of-the-art technologies. So it doesn't reinvent the media streaming, but it either uses what is already available, what was actually already available a few years at least before the WebRTC was invented. And WebRTC was also meant to bring video conferencing to web browsers because before WebRTC, the only way to have video conferencing in browser was to install some Java applet or other nightmare technology. So that's why it was focused on that when creating WebRTC. And it's still the only way to live stream, or at least the only reasonable way to live stream a video from a browser today. WebRTC also allows for peer-to-peer streaming, and it was designed in mind to allow peer-to-peer streaming between two browsers or many browsers without any relying server. So let us see how will this look like. We want to establish a video conference between two browsers. So we need a server. Wait, I said there will be no server. Well, we need a server anyway, but it won't relay any media. We want to relay any media through it. So what we will do, the server will send the HTML web page so that we can embed our WebRTC conference there. We will exchange session description protocol messages through that server. And we will exchange also interactive connectivity establishment messages. So session description protocol is a protocol that allows to specify what exactly is going to be broadcasted. Is this a screen share, or is this only audio, or maybe audio, video, and screen share? And how this is going to be encoded, what extensions maybe are going to be used. So regarding SDP, here is an SDP message, an example of SDP message. So I think we can encounter two kinds of protocols. The ones that are text-based and that are human-readable, but they occupy maybe more bandwidth, and the other ones that are binary-based, so they are hard to read, but they occupy small bandwidth. So SDP is a text-based, but it's not human-readable at all, at least for me. Well, yeah, we parse this XSDP with our we parse this SDP with our XSDP library in Elixir, and here is how it looks like. You can see that it's not flat as it may seem from the message on the left. It has at least a few levels of nesting. Okay, let's get back to our graph. SDP is definitely not something pleasant to deal with. Then we have interactive connectivity establishment. It's needed to establish the connection, the direct connection between these two browsers. So the problem with establishing this connection is usually that the browsers are behind some NAT, so it has to be traversed. In some cases, it cannot be traversed, and we will need some relay server anyway. So what are we going to send between these two browsers? We are going to send UDP packets that contain SRTP packets. SRTP stands for Secure Real-Time Transport Protocol, and it's the state-of-the-art, again, technology for live streaming. It handles things like timestamping, packet ordering, extensions for congestion control. It is all perfectly suited for live streaming so that we don't need TCP. So whenever possible, we use UDP underneath. Inside this SRTP stream, we are going to send either Opus or VP9 or 8 or H.265 5 or 4 encoded audio or video stream. So that's how it looks like when we have two browsers. When we have three browsers, it will look somehow like here. When we have four browsers, we may do something like here. When we have five browsers, we can do something like here. As you can maybe see, it won't scale because each of these participants has to send his media to all other participants. That's the mesh architecture. So unfortunately, this idea behind WebRTC doesn't scale even for average size video conferences. That's why we need a server anyway. So how do we deal with such a server? What does the server do? The server receives the stream from each of these participants, and it can either send the stream back to all other participants, so send the stream from each client to all other clients. That's the selective forwarding unit, or SFU for short approach. Or it can mix together all the streams that are sent to it and send mixed stream to each participant. So it receives one stream and sends one stream to each other participants. So in fact, the server here acts as a peer in peer-to-peer connection. So we have a peer-to-peer connection between the server and each client. So how this server needs to behave? Firstly, it has to get tracks information via SDP. What are the tracks and how they are encoded, etc. Then it has to establish connection via ICE, as we've seen before. It has to exchange encryption keys via DTLS. This is needed for SRTP. And then it can start receiving the tracks. They are in SRTP stream. Then when these tracks are decrypted, they are demasked from the RTP stream. And then in SFU approach, we can just forward the stream to all other peers, so forward each track. And in MCU approach, we have to decode, mix, and encode back the stream together. The problem with that approach is that these three steps are computationally expensive, because when you just demask the stream, you just take the binaries, move the binaries in a proper way, while decoding involves handling the compression stuff, and encoding also involves the compression, which is really computationally expensive. So that most WebRTC video conferencing server use the SFU approach, and also we decided to go that way in Membrane for now, at least. How to make WebRTC work in Membrane? Membrane is basically about creating pipelines. So here we have an example of 4 connected elements, and some stream goes from the source through these filters through the sink. These 4 elements connected that way form a pipeline. A nice feature in Membrane is that you can group elements together like that and create bins. And when you create a proper API for such a bin, then you can just hide its contents from the user. So the user sees the bin as if it was a normal element. It is particularly useful in case of complex stuff like WebRTC, because a pipeline for WebRTC server for just two peers, 2 clients, looks like this. So it's quite sophisticated. When we enclose the stuff into bins, we can simplify it to that shape. So I'm going now to switch the browser. Is everything okay? Okay. So, oh no, here we have the same. I made it look like here, but it seems the graph was reordered. So let's stick to that, to the presentation. Well, we have here 2 endpoints. The endpoints are responsible for connecting to the participants. So here we have 2 participants, 2 clients, and endpoints for each of them. In between, we have T elements. The T elements are enabling us to split or share, maybe that's the better word, the stream to multiple endpoints. So if we had multiple endpoints, like at least 3 here, the T's would just send the streams to all these endpoints. Now they send only to the one remaining endpoint. So that looks quite simple. So let's see what we have inside the endpoint bin. Here from the left, we have ICE bin that is responsible for all this ICE stuff, the DTLS and Exchange also, and for transferring the stream to RTP bin. RTP bin decrypts the stream and takes the tracks out of it and forwards it to the output endpoint bin paths. These are 2 lower paths, these dark yellow rectangles on the right. So this is basically the API for the endpoint bin. These paths forward the stream to the T's. And the other way around, we have the T's forward the stream to the endpoint input paths that are the top 2 ones. We see that here is an H.264 track because we need an H.264 parser before we pack it into RTP, and some other track, probably the Opus audio track. These tracks are sent to RTP bin. The RTP bin produces also 2 outputs for each track in case we wanted to send them in different ways. But we want to just send them via ICE, so we use the funnel and proceed to the ICE bin. And that's how it looks like. So what are the benefits of this approach? Well, here is the same graph, but simplified. Just one endpoint sending data, one track to another endpoint. So let's suppose we want to dump the stream to the file apart from just sending it to the other endpoint. So we can just add another piece of pipeline to the T. And from the architectural point of view, at least, it's simple as that. The stream is dumped to that part of through that part of the pipeline to the file. Or maybe we can publish the stream via HLS. From the architectural point of view, is the same, exactly the same problem. It's the same way of doing that. Also, if someone wants to customize the stream in a way that is not supported in Membrane, he also always can implement his own filter and plug it between, for example, endpoint bin and the T to apply some custom filtering to the stream. Another situation may be when we have two pipelines like that. Usually when we have a server, for example, this video room server, we have multiple clients and multiple rooms. So if one room fails, the other can work without any problems because pipelines are started in different Erlang processes. So that's thanks to the Erlang VM. Moreover, let's get back to our file example. When the file pipeline part fails for some reason, we can still continue streaming to the other endpoint bin and restart the file. That's thanks to the mechanism we have recently implemented in the membrane core. That's called crash groups, and is slightly different, but the idea is similar to normal supervision in Erlang or Elixir. Well, and finally, we can do what we see here. So this complex pipeline, it's indeed complex, but at least we can see what's inside it. That's thanks to the telemetry stuff we are working on. This is called membrane dashboard. As you can see, it's not really, as you could see before, is not really working stable now, but we are working hard to make it more stable and to make it show in a live manner what's happening in membrane pipelines. So when we implement some feature that allows looking at the membrane pipeline in some specific way, it will also work for WebRTC. So how does it look like specifically now? We have two packages. The first is membrane WebRTC plugin. It contains the endpoint bin that I showed you before. And we have membrane video room demo package that contains the SFU server. So the server that you can use to create a video conference using WebRTC. The problem with the second package is that it has no API for now, so you can just compile it and run it, and it hopefully will work. But any customization to that needs to be done by forking this repo and making changes. And some people already are doing that, so we appreciate the effort. So that we are now working on separating this SFU server to another package and making an API, and it's the first step of our short-term goals that we are working on now, so that this package no longer has to be forked to make any customizations, but we want to exhibit an API that can be used to customize this server for your needs. Of course, it won't be the final version of API, and I think we will have to make some breaking changes in the future because it's hard to predict how to design such API. But at least a first version we want to release soon. The next step is improving reliability and performance, of course, because we have just managed to make it work. So this is in these areas, there is always work to do. And fine-tune the membrane dashboard so that you can use it also in your projects. Our long-term goals are scaling to multiple nodes. We hope that Erlang distribution will help us here. We will also try to scale a single room in this SFU server so that we could handle a room of thousands of people in our SFU. Because of scaling it to multiple nodes, it's going to be a hard task, but that's our plan. We also want to provide a more black box API for video room and WebRTC in general, so that you didn't have to know exactly how it works internally to use it. For now, unfortunately, when working with pretty much any video conferencing server, at least if you don't want to have the most basic use case, you have to know a bit about WebRTC to use it. That's also the idea of Membrane itself, to make the video streaming or streaming in general easier and requiring less media-specific knowledge. We also are constantly working to support more codecs and extensions that make WebRTC experience even better. So that's pretty much all I wanted to show you now. Huge thank you to our Membrane team that's working hard to make WebRTC and other Membrane stuff better and better. Thank you to Software Mansion that stays behind the Membrane since its beginning. And thank you all for listening to this presentation and for being with me. Thank you.
Okay. Well, thanks for the presentation. We do have a couple of questions from the audience that I'll ask you now. So the first one we have here, so first of all, they say great project, just so you know. And then they ask if there's any support for SIP to add telephony into the mix along with WebRTC.
Oh, it's not yet supported. First, you want to support WebRTC itself, but of course, there is a possibility to bridge to Membrane. For example, if you had some bridge that converts SIP to an RTP stream, it's possible to link it into Membrane pipeline. Also, as I said, the pipelines are extendable, so this will definitely be possible in the future. But for now, we don't support SIP in Membrane itself.
Okay. So another question here is how many clients can one room handle for now?
Well, this is a tough question. It depends on the server, but it's rather tens of clients for now because we haven't done any bigger performance optimizations. But the good news are we are still working on performance optimizations, so we are able to reduce the core CPU usage by like 20% thanks to the hot path optimizations we've just made, but it's not yet published. So when it will be, I will then share the details with you.
Okay. Last question we have here from the audience is, can you build a Zoom clone with Membrane? And does Membrane have a plugin to capture the screen to share?
This video room demo that's available already has this feature to capture it supports screen sharing. And the other part of the question was?
If you can capture screen to share, that was the question. The other part of the question.
But the first part?
No, the first part. If you can make a Zoom clone.
Yeah. If we can make a Zoom clone. Actually, it depends on what you mean the Zoom clone. To handle as many users as Zoom. For now, it's not possible with Membrane, but we are going to achieve that with extending to distribution to multiple nodes. So in the future, we hope it will be possible. But Zoom by itself is just a video conferencing server, so that's what the Membrane allows to.
Okay. Actually, we do have another question here. It's again saying great tool and thanks for the presentation. I just want to mention that. And then if it's possible to use Membrane to stream interactive content, for example, have a WebSocket channel to collect inputs and then dynamically render.
Okay. Well, I don't really understand how Membrane fits here. So basically, you can use any transport with Membrane to stream the contents, but I think if it's regarding media itself, then streaming through WebSocket is not the best idea, because it uses TCP under NF, and the TCP is not well suited for streaming media in general. So it's better to use RTP as RTP over UDP as WebRTC does.
I do have one other question, kind of more generic one and less technical, just to understand what's the goal of the membrane team project going forward. What would be like a milestone for you guys to achieve?
So yeah, we have a couple actually. Firstly, we want to, in terms of WebRTC, we want to make this stable and performance, so it can compete with other SFU servers. And the other milestone would be to be able to scale, as I said before, to scale to many nodes that will open a new range of possibilities before us. And the other milestone is to make the WebRTC, and this is also the milestone for membrane itself, to make the streaming easier. For example, to make an analogy so if you want to make a website, you don't have to know how the TCP works internally, despite all the requests are going via TCP. When you want to make a WebRTC streaming server, you most probably have to know how SRTP works, despite you don't touch it directly. So we want to fix that in membrane, and this is also a problem for media streaming in general. It requires lots of knowledge because of the lack of the good abstractions that are making it easier to deal with the complex stuff. So it's not where membrane is now, but I hope it's a place where membrane will be in a year or two,
Cool.
rather two.
Yeah, I don't know if you have anything else you wanna share with us.
Yeah, thank you for these nice questions, or for being with me today. We are available via Discord, membrane Discord channel, via Elixir forum. So if you want to reach out, we're there. I will also be in this break.
The sessions, yeah.
Yeah. So if you want to ask more questions or chat, then I will be available.
Cool. Again, thanks for the talk. Thanks for being here, and talk to you soon.